Welcome to IGLUNA 2021 field campaign. Welcome to the top of Mount Pilatus in Lucerne, Switzerland. IGLUNA is the ESA Lab at CH, part of the ESA Lab initiative launched by ESA to create a hub for innovation between universities, research organizations and industry. Space Innovation coordinated the 12 teams from all over Europe and even Canada participating to the IGLUNA 2021 adventure and led the main systems engineering activities. I have the pleasure to introduce today the live stream of the IGLUNA team LUIEE of Technische Universität Berlin in Germany. LUIEE stands for LUnar Ice Extraction and Electrolysis. The TU Berlin team tackled a very challenging project seeking for ice, melting it with solar power and then separating it into hydrogen and oxygen by electrolysis. Indeed, it's now proven that many celestial bodies like the Moon and potentially Mars have ice on their surface or under their surface. Ice is a very important resource for life, of course, but also for powering the various systems required for space exploration, including the rockets. This also means many projects, complex projects out of one mission that LUIEE team managed. Please enjoy their presentation. The team will answer your questions after the presentation. Do not hesitate to post them on YouTube.
Yeah, hi. So my name is Milind Jani. I am the project manager of the project LUIEE, which is LUnar Ice Extraction and Electrolysis project.
Hi, my name is Sneha Benjamin and I'm a systems engineer and I'm also responsible for the electrical power subsystem of LUIEE.
I am Adrian Ricardes from P03, IGLUNA field campaign, and the team is LUIEE. The project is LUIEE, LUnar Ice Extraction and Electrolysis. I am part of the subsystem software development, TTNC, and also OVC.
Hello, I'm Prachit. I'm the mechanical engineer for Team LUIEE. I'm responsible for one of the payloads, that is vaporization chamber, and also the chassis of the rover, and in general the mechanical interfaces that we need throughout the system.
My name is Matvey. I developed LUNar payload for LUIEE mission, and yeah, that's me.
Sure, I'm Marco Bermudez. I'm in charge of the test development and the PR in the group, in the LUIEE team.
Right, so this project basically started from since last year, which was 2020, and one of our supervisors made us know about this particular campaign, which is IGLUNA campaign. So as those times were a bit difficult for us because everyone was under lockdown and there were corona restrictions, so we were all located at remote locations. So with this particular campaign, we first formed our team, and then we we did some mind mapping and brainstorming about what exactly should be the idea of the project, and later on we sum up into a common goal that we would like to achieve, and then we realized that okay, we should work on a project which is based on rovers, and it should also help in long term for extending this particular project to a lunar scaled projects. So basically, our initial idea was just to develop a system to have to melt the ice on the lunar surface and to collect that particular water ice. So we had several other options like drilling the lunar surface and other things. However, we thought that we should be able to use the renewable source of energy, like we have sunlight over there on the moon, so we should use that particular energy to melt the ice rather than depending upon the high volt batteries and other things. So that's something that we thought of, and then we decided that we'll go with the lens and mirror mechanism, and we then designed another payload for a collection of those vapors. So this is how we came up with this idea, and then we thought that maybe a mobile system will also be really helpful. So we then thought of combining all these payloads onto a rover so that we can demonstrate a mobile rover operation.
Well, So the rover is intended to collect water on the moon. So on the south pole of the moon there are places so-called peaks of eternal light, where we have a lot of light, and in the craters near them we have ice inside the crater holes. So what we plan to do is vaporize this ice and then collect it. What we need basically is an enclosed surface which can contain the vapor, and a surface which can exchange heat and condense the vapor, and then also to collect it. So that's where this comes from. The design is similar to a solar still, yeah, that's it.
Sure. So at the bottom you can see a block bearing, which allows the rotation in the azimuth angle, and we achieve this rotation using the system of gears. Right now you can see only the big gear installed, but basically we use a stepper motor to rotate the reflector. Above the big gear there is another stepper motor with a lead screw, and as it turns the elevation angle changes, and we can control these motors very accurately.
Okay, so the EPS architecture remains the same for both the rovers, but there were some design changes that we had to make for the bigger rover, that is the LUIEE. As you can see on the smaller one, we just had one battery which was powering the locomotion as well as the electronics and sensors. Whereas on the bigger rover, we are making it a bit more complex. We have two batteries, each of 14.8 volts. One of them is powering the locomotion, and the other one is powering the electronics as well as the two payloads that we have over here, the lens mirror mechanism as well as the vapor chamber and its deployment. And also for the smaller rover, we had a less complex or complicated power conditioning, but for the bigger rover we have almost 3 DC-DC converters. Two of them were 12 volt DC-DC converters, whereas the other one is a 5 volt one, which would condition the 14.8 volts to the required voltage levels. Okay, so LUIEE stands for LUnar Ice Extraction and Electrolysis. So electrolysis is a big part of our project. And why exactly it's needed? Because there is tons of water ice on the north and south poles of the moon. And we are concentrating majorly on the south pole where the Shackleton crater is located. So on the rims of the Shackleton crater, you have continuous sunlight throughout the year. And we wanted to harness the solar energy that we get at the south pole and use that to melt the ice. And once the ice is melted, we would be needing to produce oxygen and hydrogen for the astronauts. Basically for transportation, hydrogen can be used as transportation or rocket fuel, and also it can support the life systems such as providing oxygen as well as water for drinking purposes.
Yeah, of course. Okay, so as an overview, the navigation is done by using an image and comparing the coordinates on the X and Y, and using the sets for the risk mitigation, as I said before. So this navigation is performed by using a PID controller. When you are moving your motors, you can actually try to center the point so that you can go straight forward. This is more or less how the navigation is done.
Okay, so talking about the testbed, we can see it in here. So it has several components. It has a ramp, it has a platform, and then at the back it has an extension. So the idea is to have modularity first. We just gotta assemble it really easily. We just gotta store it really easily. So that was one of the principles. We were inspired by some of the lunar missions that have already brought a similar testbed.
At the beginning, LUIEE was just two payloads, the one lens and mirror and the second one the vaporization chamber. And we have a really good heritage of space rovers at our University TU Berlin. So we were going to use one of them as our platform. However, due to the pandemic, we were not able to access it that frequently. So we decided to make our own rover, which is easier to build, which is modular and can be reused, and also be made up of most of them by commercial off-the-shelf components. So that was the first evolution, that we had to go from no rover to make a rover. So we designed a modular and easy to build system which we are using right now. And the payload that I worked on, the vaporization chamber, it is what it does is gives a restricted volume for the water vapor which has been created by the lens and mirror mechanism to condense. It condenses the vapor, converts it into water and collects it inside, and then we have other things like pumping the water out, measuring how much we got. So those are the subsystems.
So we inherited the design from our German counterpart from planetary exploration course, and at that point the design had a few problems. Azimuth control was involved very heavy and big parts, and we couldn't manufacture them, especially in Corona times. That's why we had to redesign a lot of aspects of the system.
So initially we started off with a mini LUIEE that you can see over here, and we designed the electrical power subsystem for it. And once we were sure about the challenges that we would be facing, we wanted to scale it up, and then we went ahead with the bigger rover.
So the evolution was starting with a smaller rover. We created this small prototype because it was similar, the architecture and also the structure. We started with the first software development so that we can in the future scale it up, as you can see right now with the bigger rover, and migrate all the subsystems and the algorithm. So it worked, and we are very happy about it.
So the first and foremost thing that we were expecting was the manufacturing. So as during the Corona situation, the universities were closed and also the workshops were closed. So this is something that we were expecting, that we won't be able to have the manufacturing done rapidly at the university. So we heavily depended on the COTS components, and then we also made a quick change over manufacturing it in-house using 3D printed parts. And this is something that we did it over time.
And talking about the status, we already have the modified systems ready. We would like to in future keep on working on the original designs that we have, manufacture them over time, and then keep on testing them as well. As of now, the simplified systems that we have brought here, we have tested them separately, we have tested them with integration, and we are happy to tell that they work exactly as expected.
So I think at this moment the Lucerne is complete to the point when it can hopefully meet the requirements and extract the ice.
Yeah, okay. So we have this link, simulated link, that is, there is a distance between the Earth and the Moon, so we have around 1.3 seconds of delay, and also we have this limit of 1.5 megabits per second, so we have to take into account several features of that link. So at the control room we are managing the control mode, and in this control mode we are using a GUI, graphical interface, to basically move, deploy the payloads and also move the actuators and receive the sensor data from this rover. So this is the main idea.
Initially we wanted to do the testing here because it's a mountain environment and it would be similar to the moon. However, you can see it's summertime and we don't really have any ice. And the idea is to have a receptacle in which we put ice, and of course with the lens and mirror payload we're gonna test it and melt it. However, not all days are really like this, so because of that we have a redundancy measure called the electric hot plate. So in this case, if we don't have any good weather, we should be able to still melt the ice and be able to fulfill our objectives.
Yeah, so as you know that we are a team of 6 students and we are all pursuing our masters in space engineering. So to have completed such an ambitious project and to withstand the success criteria that we had originally had for us, we then merged this particular project into our several courses within our master's program. So one of the courses was planetary exploration. So we encouraged students, and also our supervisor played an important role in that. They encouraged students to participate in that particular course, and we got more hands on this particular project. And because of them, we were able to timely finish all the things that we were planning, and we were able to keep the timeline on to progress, and we were not delayed much.
Okay, so in this case we have several kinds of partners. So for example, we have our academic partners. In this case we have the Technical University of Berlin, and in there we have the Masters of Space Engineering program. So it has been really supporting us with some guidance. Our supervisors are from that program, so they have really been pushing us to go further. Then we have some IGLUNA campaign partners. So of course we have a Space Innovation, and in any of the reviews we have had some supervisors from different universities in Switzerland. We also have some supervisors from NASA JPL, from ESA. So in this case they are providing us with real challenges. They're asking us tough questions so that we can be better prepared. And last but not least, we have our sponsors, so they play an important role. In this case, we have B-Space that is providing us some budget. Also, they're providing us some supervision, so that is really helpful. We also have an APTER. In this case, we have a subsystem that is the electrolysis kit. So in this case, they are providing us guidance with that. We also have Orion in this case, so as you can see, some of the parts are 3D printed or additive manufacturing process. So in this case, they are helping us set up this whole subsystem. And of course, we have orbit recycling. So in this case, they have been really helpful with the lens and mirror mechanism. We've been having several Zoom calls and some meetings in order to set up and make it function for the final review.
Okay, so one of our sponsors, Enapter, had hosted an event called the Generation Hydrogen 2021. It was a platform where hydrogen experts from all the industries came forward and presented their work, and we participated as well, and our project was presented under Hydrogen Aviation and Applications in Space. And we presented Project LUIEE, and it was a really great opportunity for us to reach out to the experts from the industry. There were 15 panelists, and we got a lot of feedback, a good feedback, and we have tried our best to implement it in our project.
So as from the academic point of view, as we were studying and also doing this project in parallel with our studies, we would like to extend the current state of the project by proving the concepts that we had in our mind. So now these 2 weeks of the field campaign will let us know about the results that we will be obtaining from the different payloads and the rover operations that we were doing, and based on these results we will scale it up further to make the systems more and more sophisticated. And such reviews like the IGLUNA organizers have organized for us, those reviews can help us in designing more and more sophisticated systems which can withstand the harsh environment in lunar surface.
So from the design perspective, we already have designs which can be directly used for the moon. We have not had opportunity to manufacture and test them yet. So that would be our next step, to go ahead and manufacture the designs that we expected for the lunar environment, to assemble them and to test them in similar situations.
Okay, so the next steps. This could be, of course, scaled up in the future. I don't know how many years, maybe between 5 or 15, maybe 20. But of course, this idea is not only optimistic, but treatable for the future. And we can use the same idea of using the payloads to extract water from the moon. And the communication is the same principle. We just have to rely on other software tools, middlewares, or also some devices that are space rated. Yeah.
So since this is a relatively complex system, one of the more important learning objectives was to know how to bring the systems together, how to make the interfaces work, and how changes in one system affect the other. So the systems engineering tasks have been a really good learning curve. Next, we also had to design our systems for additive manufacturing, because we had to optimize the parts so that they could be printed the right way. So that was another important thing that we learned.
So I would say the main outcome for me was a lot of CAD design. I learned a lot of SolidWorks and how things that look good in CAD doesn't always work in reality. It is very, very difficult to make, especially an optical system, work, move, and align properly.
So this was a very good learning curve for all of us. This is an international platform that IGLUNA has provided us. We have got the opportunity to meet several different teams from all across Europe and even from Canada. So it is a very great, it's a good platform for us to showcase our project, and we have learned a lot in the last 1 year. And thanking the sponsors who have contributed so majorly to reach, to make us reach where we are today, especially Enapter for providing us the electrolyzer kit, Orion for helping us with the additive manufacturing, and then we have the Orbit Recycling who provided us a lot of technical guidance regarding the lens mirror mechanisms, B-Space for supporting us throughout each and every phase of our project, and also last but not least the MSc department, who have been consistently helping us throughout the COVID phases and providing us all the support that we need to make this project a big success. So thank you all for the support and guidance, and we hope that LUIEE would be able to go ahead further and to infinity and beyond.
So first of all, I would like to thank the IGLUNA organizers. So they helped us a lot in providing technical support and also the logistic supports that they are providing, and also our academic supervisors who had helped us in difficult times such as the COVID restrictions were there, and they provided us all the lab support and everything that we need. Without even if we have a restriction at the university, we were given the equipments to carry at home, and we were doing everything offline. So this is something that we definitely are grateful for from the supervisor, and also about our team. Team has done really well, and because of the team and all the other students who have participated in this project, because of them this has come to a reality. So thank you all for your support.
Team LUIEE, thank you very much for this very interesting presentation, a very challenging and complex project. You also managed successfully your contingency, like building a rover from the scratch to replace the foreseen on one that became unavailable. I'm impressed by the quality of your work and your motivation. We have time now for questions. Please do not hesitate to put them on YouTube. On my side, I have a first question. What were the most challenging aspects of your project?
Okay, so since the beginning, when we started this project, we started gathering the team like who all are interested in participating in this project. So at that point of time, as you know, Corona crisis was at the peak, so everyone was at their home countries, and we then had to organize and arrange everything remotely. So that was one of the most challenging aspects that none of us have had an experience of working remotely and managing the project remotely. So that was something that was a bit challenging initially, but later on, as the restriction got relaxed, we were able to meet together and do some other things while working on the project. So that is something that we worked out. However, there were some other restrictions which were still there at the university for the several aspects of having the just the restrictions that university has to have for preventing the extension of the corona. So this was something that had severe impact, but maybe the other teams members might have also some points to add. So you can also, maybe Prashit can give some more info.
So like Milind said, the pandemic has obviously been a big challenge because of accessing and meeting together and other things. But from design point of view as well, we had to face a several challenge, and there were that COVID situation also made it very difficult to access workshops and have it
things manufactured traditionally, and that's where additive manufacturing came into picture, and that's what has really enabled us to bring this project here today. And few of our sponsors, our coordinators, our academic supervisors, they have helped us a lot to go through this. We had to design most of our aspects for 3D printing so that they can be manufactured, and that has been a major challenge that we had to overcome.
And also, maybe Sneha, would you like to add some more thing related to how the labs was set up at our home and something like that?
Okay, so while we were working on our project, we had restrictions at the university to access the labs. So basically the entire electrical wiring of this rover was done at home. We set up a remote lab, and we requested our supervisors to help us with soldering equipments and anything which we did not have access to. And luckily it all turned out well, and now you see LUIEE over here.
And just concluding, like we covered the mechanical aspect, the electronics, maybe we can also have a quick word from Adrian related to how the software was developed under this situation.
Yeah, thank you, Milind. So regarding the software development, also it was a big challenge because we didn't have all the hardware available. So we started performing some small tests, as you can see in the mini rover, in this case called Mini LUIEE. It was really useful during our subjects, during the first milestones. So we presented how the navigation was working, how the basically the operation, the steps that were performing were operated, and also testing the link. So everything, let's say the first months were simulated, and after that we were able to migrate all the systems to the big rover, and here we are. Yeah.
Very good, very good. In fact, what did you prefer to do during this project?
So from the technical point of view, the first and the foremost thing was the requirements and the risk analysis, which was the crucial aspect for any of the projects. And this is something that we were learning since our master's program, that we have to have our requirements fully understood so that we can build upon those requirements and then create our own success criteria. From the project management point of view, or being as a representative of the group, this was something that I was more inclined towards, and definitely the other team members might have some more views on that. So maybe Marco, would you like to share your views?
Sure. So this is really a good question. I really like it because I don't know, we had to think out of the box. Like really, because of these conditions, we had to think of some other ways to do our project, like how do we wanted to convey our objectives and really get to here. So I think everybody went and I don't know, the brainstorming sessions were really fine. We got some really cool ideas, and at the end we were able to really performing here. So I hope you saw the video, and we have some nice results. So Matvey, would you like to add something?
Thank you, Marco. I would say that my subsystem, lens and mirror, I mostly enjoyed the practical part, building it, working with my hands. It was a lot of fun. Thank you.
Thank you very much. In fact, the final target of your project is to go to the moon. And how LUIEE system will impact on the concept of human settlement on the moon?
Yeah, so as LUIEE stands for Lunar Ice Extraction and Electrolysis. So, as mentioned by Gils earlier, that ice is an important aspect for human to survive, and the most critical aspect for any human to survive is water and oxygen. So this LUIEE system is able to melt the ice, and we can get a water out of it, so which is one of the crucial aspect. And another crucial aspect to live on the moon is to get the oxygen, so that the astronauts does not have to rely completely on the resources that are coming from the supplies from the Earth. So using the electrolysis process, maybe this particular aspect can be achieved, and this will be able to make the astronauts independent to stay in the lunar environment. So yeah, these are my views, and maybe Sneha has also worked a bit on the electrolysis process. Maybe she could also add some points on this.
So, like Milind mentioned, LUIE stands for Lunar Ice Extraction and Electrolysis. And in order to have a sustainable moon village, the astronauts need to rely on the local resources. And as you know, the north and the south poles of the moon have a lot of water ice. And they can harvest this water ice and then split it into hydrogen and oxygen. So, hydrogen can maybe be used as a rocket fuel. So the astronauts do not have to carry the extra fuel all the way from Earth to Moon. They can just fuel it on Moon, and maybe that could be like an extraterrestrial gas station. They can just go on to the next journey into deeper space. And the oxygen can also be used for breathing purposes. And water, you know, it is a life source. So it can be used for drinking as well as for growing nutritional crops. So those are my views. Prachit, would you like to add something?
Well, yeah, water is the most important resource in space, right? We use it for drinking, we use it for our food, and we also use it for rocket fuel. So the system that we aim to develop is that it takes care of all of these points, so that once it becomes space grade, all of these questions can be answered. So yeah, that was our motivation behind it.
Thank you very much. Now I have a series of quite technical questions from your colleagues probably at the ground station. First one is, any chance to make this open source?
Okay, so maybe Adrian can have a better clarity because he has worked on the software. So maybe Adrian.
Okay, open source. As you know, there is a software called Robot Operating System, ROS. So we are using this software that is open source for everybody. There are several tools, not only this, but also available on the shelf on the internet. So you can keep in touch with the developers and also from around the world, not only your colleagues from the institute. So in this case, modularity is a crucial point for the open source thing. And apart from that, of course, we can scale this up to bigger rovers or smaller rovers on Mars or on the Moon. So this is the future, basically. And it's possible, open source, of course. It's already implemented, modular. So, yeah.
Thank you very much. In fact, I think you also answered another question related to the software platform.
Sure.
There is another question related to more on the mechanical side, on the buggy itself, on the rover side. Did you try the mesh wheels as Lunar buggy had?
Okay, maybe Prachit can answer this question.
So actually all of us from TU Berlin, and TU Berlin already has a very good heritage of space robots. So there are much more advanced robotic platforms that are already developed at our university, which take care of different kinds of environment, different celestial bodies. So the aim for us was to develop a payload and to deploy it on one of the already ready platforms that we have at our university. But like Milind said, due to the COVID restrictions, we could not actually access the rover that often. And therefore we had to create a modular rover which can simply just help us support our payloads. So when you talk about LUIEE, it's mainly about the payload, and this payload is modular enough to be used on any rover. So there are many systems which are much more efficient to be used on different celestial bodies, and they can directly be integrated with this payload. So I would say we can definitely use any kind of mesh wheels and even rocker bogie chassis and suspensions and many things, but that's already done at our university. So what we do is go a step beyond that, even further of that.
In fact, another question related to that, what will be the expected speed?
So currently the expected speed of it is only about 0.5 meter per second. That is the maximum speed, but that is not a problem for us, because more importantly, the important aspect for us is to have stability in motion, because we have some of the suspended payloads and we do not want them moving around. And once the rover is in place, it stays there for at least an hour or so for the operation. So speed is not our priority, but we have made sure that our motors are high torque so that we can carry a lot of load in most of the environment that we work with.
And what is the duration of the batteries? How long the battery can last with these operations?
Yes, maybe Sneha can answer this.
Okay, so we have used two batteries, and one of them is used to power the locomotion motors, and the other one powers the electronics and supports the payloads. For example, it supports the lens mirror actuation as well as the vapor chamber deployment. So each of these batteries are having around 14.8 volts, and as per the test that we have conducted over the past few days, I think the batteries can last all day long. So that's a good thing.
Okay, thank you. You have a quite large payload on this, and there is a question on how wind stable is it?
Maybe Mathway has designed the structure, so maybe you can have a better idea.
You had, in fact, the opportunity to test it last week.
Actually, there is a wind tunnel at our university, but unfortunately we couldn't negotiate the time slot for testing because of the corona. It was very, very difficult. So we made sure that the system is sturdy enough that we can withstand barely perceivable wind. But of course, it would be unadvisable to use it in bad weather. So for now we just we have a list of constraints, and one of them we cannot operate the rover, at least with lens and mirror, in high wind. Thank you. Exactly, and of course there is no wind on moon because there is very thin layer of gases.
But on the moon you will be on the pole, because ice is on the pole. How do you collect the sun on the pole?
Okay, so on the south poles of the moon, there's this huge crater called Shackleton crater, and the rims of this crater has sunlight throughout the year. So instead of using smaller reflectors, maybe we can increase the size of these reflectors, and those can be used to concentrate the light from the sun, and it can be directed towards the inside of the craters. So that could be one way to direct the sunlight into the craters so that we have the space for working with the smaller rovers.
And in fact, a related question is related to the solar energy. Did you think on how to use this solar energy for other purpose with your equipment? There is a question, literally it's written, is there the possibilities to develop the use of solar energy?
So yeah, one of the aspects, like one of the application of the solar energy you see based on the system that we are melting the ice using the solar energy. However, the future plan of this particular rover is to have solar panels also attached to the rover so that the batteries can be charged automatically. Currently, we are using an external battery charger. So another application of using the solar energy would be to continuously recharge the batteries using the solar panels, and yeah, in that manner we can increase the lifetime of the rover so that it can operate in a much longer duration.
Thank you very much. When I am looking at your rover, I have another question: is where will the samples be stored?
Yeah. So Prashit, yeah.
Yes, so that's a good question because that explains our rover a lot. So we have two payloads. One of them is the lens and mirror, like Mathway explained, which is here, and the other one, maybe you can see it in front, it's called the vaporization chamber. What it does is, so basically the way it works is the lens and mirror collects sunlight, gives us a lot of heat to work with, and it also directs the heat we want it to. So the heat goes to the bottom of the rover where there is just bare ground. What we do is the second payload, it looks like a dome enclosure. It goes and sits on top of it, and once the ice starts evaporating, the inner sides, the inner surface of the dome is basically a condenser. So since we are here on Earth, the vapor gets converted into water, and we store the water in an annular ring around it, which we can pump it out later. There are outlets with given inside the payload which can let us take the water out. However, this is not the problem on the moon because vapors don't turn into liquid on moon, they just directly go back to ice. So it's very simple that the ice can directly still be collected on the surface itself. So for operation here on Earth, what I can say is the water, about the storage you asked. So the storage is already inside the payload, so that we can lift it up and take it away and use it wherever we want it to.
Thank you very much. In fact, I think you answered several questions related to also to the possibility to extract, how to melt the ice, and so on. I have a question related. The rover standing in front of you, is it ready for going to the moon? And the further question: what shall you do to go to the next step to improve your system or to make it moon compliant?
Okay, so maybe in this particular question we can divide it into mechanical, electronics, and software based. So we would start with the software based on the current navigation that we have. So maybe Adrian, you can start with the software.
Thank you, Milin. So yeah, regarding the software, it is modular as it was stated, and not only the modularity is available in this case, but also the architecture is available. We are using commercial off-the-shelf, in this case CPUs. Also we have microcontrollers, we have sensors, so we should take into account in this case space-rated devices. Also for outgassing, for example, that is a huge challenge on space. Also the temperature range and so on. So this is one of the points. And also regarding the software, we just have to take into account the link that in this case takes 1.3 seconds more or less from here to from the Earth to the Moon, and also we have a restriction of data. So this could be, yeah, of course, taken into account. Yeah.
And yeah, in addition with the rover, we also have a test bed. So maybe it is good to like rover is of course we are seeing the rover currently with the test bed is down there. So with the rover we also need the test bed. So maybe Marco can give a more insight about, in addition with the rover, what all changes maybe we need to do for the test bed.
Sure. So I really like this question because when we were doing research on what are the components that we really needed, with some of the missions already using it. So for example, there are already lunar missions using kind of test beds. So the idea is to reduce its weight, so maybe increase its size so it can withstand a bigger rover with bigger payload, so it could function for a longer time. But the idea is to revamp it, to really increase the capacity of it while decreasing the weight. So I would say we already have some really good ideas, and yeah, we'll be able to do it.
Okay.
So thank you. This brings me maybe to technical question asked by your colleagues. What is the material you use for the 3D printing of your prototype?
Yeah, so related to 3D printing, we have most of the components 3D printed for lens and mirror structure. So maybe Matwei can give a brief idea about it.
Thank you. So mostly we used PLA material, just because it is very easy to use. We can print fast, we can test the parts, and then solve technical problems, redesign them, and test again. It was a very long iterative process, and of course PLA material is not space grade. It will outgas, it melts at a relatively low temperature, and we used it just because it was accessible, cheap, and it works. Additionally, we used a few parts, a few critical parts made out of the PEEK material, and our I'm sorry. We'll continue. Our sponsors helped us to print and design some parts, and PEEK is a very sturdy, very robust material, and it can be used in space and on the moon. Thank you.
Thank you very much for the answer. There is another question related to communication. What is the distance that the robot can be controlled from?
Yeah, so Adrian, can you give a brief idea?
Okay, so this is a really good question because it's related also with Wi-Fi. So we can connect locally and also externally, in this case the communication between the computer that is inside of the rover. And it doesn't actually really matter how much distance we have between the testbed and also the control room, as long as we have the communication of the IP address, for example. And in this case we are just traveling some few kilometers, so it could be tested at 20 kilometers, 50 kilometers. It depends also on the structure and the protocols, but yeah, it could be tested right now.
Thank you. Maybe I have another question related to the sensor. How can the integration of sensors be implemented for a real rover in the moon?
Yeah.
And
So
what are the sensors basically you have on the rover?
of course. So yeah, most of the sensors were integrated by Adrian. So yeah, Adrian, you can go ahead.
So far we can implement a lot of instrumentation. For example, solar vector sensors, star trackers, but right now in this particular rover we are using temperature sensors because measuring the temperature is critical in this point. Also LDRs that are measuring basically the intensity of light that is received by the lens and mirror mechanism. Also we have voltage monitor to keep checking the batteries that they are in an acceptable voltage level. And yeah, we can of course implement a lot of sensors, for example encoders, to measure the distance that the rover has traveled. But yeah, so far these are the sensors, and also an IMU that checks the magnetic north of the Earth.
Okay, thank you. You are speaking of the temperature. What temperature range can this rover be used?
Yeah, so mostly the temperature is like the payload which is dependent on temperature is the vapor chamber. So Prashit, would you like to give some insight on that?
As long as the payload operation is concerned, it can take the lunar temperatures right now as well, because the aluminum that we used is actually space grade aluminum. Not only it was available, but it was also possible to machine it. So electronics and other things are have to be taken care by the thermal insulations and other techniques. But as long as payloads are concerned, they can still be worked in the lunar environment as they are right now.
And also related to electronics side, currently as this particular rover is being demonstrated on the Earth environment, so we have not selected the components which are space grade. So in case if we want to scale this rover to a lunar based rover so that it can withstand that particular harsh environment, then we might have to go forward to buy some space grade components and replace the current COTS components with them. So yeah, this is something that might have to be changed.
Okay, thank you. And how are you controlling the LUIEE rover? Is it completely autonomous, or are you able to control it manually?
Yeah, so Adrian, can you give a brief idea about it?
So it was stated by Prachit that we had a good heritage at the TU Berlin, in this case the development of rovers, and we have one subject called planetary exploration and space robotics. So some members, some students helped us on this development, in this case the graphical user interface. We are projecting it on the control room and controlling it with keyboard or specific commands. So we are receiving the data from the sensors, and also we can have a feedback from LUIEE. In this case, we are seeing what the rover sees, and it has 1.3 seconds of delay. So this is a really good simulation.
Very good, very interesting. And another question: do you know when you might be able to send this to the moon?
Yeah, so maybe Sneha can have give a brief idea about seeing the current status and what all changes can be made about it.
Yeah, so right now you see just one rover. Maybe if we have to scale up this project a lot more on a lunar mission, we can use a swarm of rovers. So all of the rovers would have a common objective of extracting the ice. And that way, once we have a swarm of rovers, we would be able to collect a larger amount of ice. We would be able to get a lot more extraction of water. And basically, if the payloads are concerned, the sizing of this reflectors you can see is completely based on the rover size. So if we have no rover restrictions, then we would be able to increase the size of these mirrors, and that way we would be able to extract more and concentrate more sunlight onto the ice. And also regarding the vaporization chamber, currently since we are on Earth, we are testing it under Earth conditions. But in future, when we have to scale it up, we can test it under vacuum conditions so that we can try and simulate the lunar environment. So this is the scalability for our project, and I think down the line, maybe after the evolution of this project and the continuous work that multiple students in the future would be putting in, we would be able to send this on the moon maybe in the future. Definitely.
Will you continue to work on this project?
Yeah, definitely. As we have good results related to the system that we have developed until now. So whatever things that we have expected since the past few reviews and whatever success criteria that we had in mind, we were able to successfully achieve them. So yeah, definitely it is a good start for us, and maybe to scale this rover from this stage to another stage, we might need to recruit more students, so that we get more hands on, and we have some dedicated team to work on a specific subsystem. So that is something from the team point of view. However, maybe Marco can give some idea related to the supports that we might need to scale this project and keep the project working for in the coming years.
Yeah, sure. So what I would like to say is it really started everything with a group of enthusiast students. So the idea is to keep on looking for this kind of students. We already have collaborated with them in this year. So we have several temporary members, and we are proud of the work that they've done so far. So in this case, we know what's requested. We have already set up collaborations with academia, with the industry. So in this case, I feel pretty confident to say that we are gonna start developing even further our projects. So the students are really in there. We just gotta get in touch with them, but we have really enthusiastic people working on this.
You are speaking of students. It was a student project. Did you thought a little bit on a business case of a future product you may develop further, some kind of roadmap for going toward the product?
Yeah, definitely. So probably Marco can also give a brief idea about that, because he has worked on business model of this. So yeah.
Okay, so the idea in this case is we of course look at the business model, and this is a roadmap in which they are looking to develop these projects and really bring it to the lunar surface in 10 years. So of course we are looking into this. There are some really exciting opportunities, and of course this is still developing a field. So what we would like to do is to continue furthering our collaborations with academia, with industry, so that we can have better results. We can scale it up, and then we're gonna look at the business side of the project, and we can really take it to the next step.
With this particular aspect, I would also like to add on one more point, that currently we have developed this system with a course of 1 year. So currently, whatever we see over here, our main aim was to have the proof of concept proved in a manner that it can be scaled further. So once like since few weeks we were testing the system, so we have some results with this, and in order to before pitching the idea to some organizations or companies, maybe we would like to make the systems more and more sophisticated before pitching the idea to the companies. And then once we are confident enough about the system that okay, it can withstand any of the harsh environment, then maybe we can have a look into what exactly would be the business side of it. But currently we would more focus on proving the concepts and making our system work in any condition. Yeah, and Adrian also has.
Okay, so actually one complementary point for this is that during this IGLUNA field campaign 2021, we focused on the mission success criteria. So we stated several points of the mission objectives, also what were the sub-objectives, which results we have. And for example, this rover is semi-autonomous, but of course it could be scaled up for an autonomous navigation, another chassis, several collaboration with institutes or other scientists. So yeah, we focused on this IGLUNA, and we got some good results about it. Thanks.
So thank you very much. Maybe the time for a last question. In a few words, what did you learn during this project?
Yeah, so maybe all the members will answer these things, but from my point of view, as this project started last year and we were in our first semester, so we were learning how space missions are planning and how things should be planned in order to have the project get successful in all the tests, maybe the acceptance test, qualification test, and also in the field. So during the this IGLUNA field campaign, during the course of the 1 year, we were put into several reviews where the experts gave us some valuable feedback on the systems that we have designed, and also some feedback on what things can be done in order to make the things more scalable and more realistic. So this is something that was a good experience to learn in addition to the something that we are learning in our university. So this was some additional knowledge that we gained, and maybe it will be really helpful for us to work on major space related projects in future. So this is something that I learned from this particular campaign. Maybe other members can also give their views on it.
Okay, so while we were working on this project, we got to collaborate with many industrial as well as academic partners. And one of the really important events for Project LUIEE was when we presented it at one of our sponsors' event in APTO, which hosted the Generation Hydrogen event. And we were presenting Project LUIEE under the hydrogen applications and applications in space. So our project got a lot of feedback, and we tried our best to take all those feedback from the panelists as well as the industry experts, and we've tried to implement them as much as possible in this project. So that was one good platform where we got a lot of inputs, and we were able to show the results.
Yes. So the thing about the things we learned, we had a lot of technical things to learn. We learned about design, going from requirements to design to manufacturing, testing. All of these technical things were a really good learning curve, and also different design reviews provided by the space innovation throughout our IGLUNA journey were very useful. The experts from NASA JPL, from EPFL, from European Space Agency, they have been telling us about, giving us constant feedback about the technical aspects of our project, which was extremely useful in making this what it is today. And also, as you can see, we are a team from around the globe. We are a multicultural team. So that was another thing that we got to learn, how to work in an international team, how to make things work. That was a really good learning experience for me.
I would like to say collaboration, adaptability, and really modularity. I would say that's the name of the project, or the keywords that we wanted to implement in here. So that allows us to really keep up our game while the conditions might be adverse. So really that's our best learning outcome.
Okay, yeah, from my part, I would say the communication is really important, always important between the team members, the supervisors, the reviewers, and also the interaction with people that you are explaining your project, how to say in few words how it works, and also so that you can know, technically speaking, to how to develop this project in the future for also other developers. So student documentation is also hard. I learned a lot from that. But yeah, it's a good achievement, and also technical part is it's deep. So yeah, please.
Thank you. I've learned a lot of SolidWorks and how technical things that I design not always work in reality. We always learned the importance of testing and building real projects. Thank you.
So thank you very much. Thank you to the LUIEE team. So many thanks also to Mount Pilatusbanen, to Lucerne Verkehrshaus for supporting and hosting us, to the whole space innovation team, and to all of the people who supported these exciting projects. And of course, many thanks to Swiss Space Office, which funded the activity, and to ESA, which initiated the activity and provided great support, mainly through experts. See you soon.